Welcome back, everyone. I hope you had the time to go to the bathrooms, get something to drink, have a little snack, grab your best coffee, and now we're going to work on deep learning. So, like a sum up of what we did so far, we are now at the point number 5. We had the hands-on on data processing, we played with indexes, with machine learning, with performances. Now what's left is basically some hands-on on deep learning and GeoSAM. And again, we are still working on the FlowGet datasets of the fire in Greece. So let's go to the part 5. So if you go to your Google Drive, my drive, the dev kit. If you go to the notebook here, number 5, we're going to work now on the deep learning part and then the GeoSAM. So if you open the part 5 with Google Collaboratory, you arrive to that part. So I already connected mine, actually. So I went ahead of you because I wanted to train a model during the break. So there is one step that actually takes around 15 minutes to make sure it actually works. But we're going to go through that. So one thing that I would invite you to all to do is connect your Jupyter notebook. And you might notice that this one actually stands something like called T4. I think by default, actually, you don't have the CPU, but you have the T4 NVIDIA GPU. So if you check the run times, basically now we are playing on GPUs. Why is that? Because when we train neural networks, you have millions of parameters. You have to backpropagate from the loss to the input and change the weights. And this includes like a lot of mathematical operations that run way faster on GPU than on CPU, like order of magnitude faster.
Yeah.
So
for this one, we need to install Colab.
We need to install Colab. Oh.
Yeah, because it's different. For me, it's different. Doesn't show. Let me. You see, it's different.
So if you do right click and open with Collaboratory,
there's no. You need to collega, connect other, and then I'm searching Colab.
Okay.
And then probably install it. I don't know what's the difference from the.
I don't know. Good questions. I don't have that issue.
No, I didn't.
I have that issue as well.
You have the issue? Who does not have that issue? You do not have that issue. Okay.
It
works this morning. Yeah.
I'm on my browser, so.
But I can install it.
But I don't think it's necessary to install it because you
Collaborate.
It's installing like in my.
Okay.
Right.
What I will do is that I will actually also copy that link.
Can you? This one?
Anyone online has a similar issue, maybe?
The machine is saying that if you simply double click on it, is it not working?
It opens a text.
Okay.
Okay, but I installed Colab and it works.
Yeah.
Okay.
So now it should work.
Okay. Maybe like this plugin.
Yeah. Weird. Okay.
So you may need to reinstall install Colab for those ones.
Okay.
Maybe because it's on GPU.
No. Good point. But maybe another way is actually to access directly to the file I sent on the chat, and I think this one should directly lead to the to that Google Colab, the Jupyter notebook. It's working, right?
See.
Perfect. It's working also for you, Alan?
It's opening. Yes.
It's opening.
Yeah.
And you are connected to the T4 GPU by default?
Yeah.
Okay, great. Yeah. Maybe it's because of the GPU. Right. Okay. All right. Are we also good here? Okay. Let's proceed. So now we're going to work on like the deep learning aspect. Training semantic segmentations using a model called DeepLab v3, which was one of the most famous deep learning algorithms for semantic segmentations based on convolutional neural network. And then we're also going to train a BAM-CD model, the model that has been defined by the FlowGet dataset. Main difference is that DeepLab v3 just expect one image as an input, and BAM-CD actually expect the two images of pre and post fire. So that's why I think it's really interesting to work here. So let's go through that process. The first one is basically again to mount the Google Drive to get the data, install the required packages. You might see that now we actually have different packages. We don't only install the H5 libraries, but also the PyTorch Lightning and the Torch Visions and TensorBoard. So PyTorch Lightning is a wrapper on top of PyTorch. So there's two main libraries in Python for deep learning, which is TensorFlow. TensorFlow is made by Google. It's really efficient for deployment of models on edges, on cloud and everything, but it's a bit more difficult. It's less Pythonic than PyTorch. PyTorch has been built by Meta, so Facebook, and it's a bit more user-friendly and it's more similar to other libraries like NumPy, for instance. So it's preferred in the research field to actually use PyTorch, while maybe developers might prefer that develop like software and solutions might prefer TensorFlow because they have better access to graphs of how neural networks is actually processed and can be faster and more efficient when deployed on edge or cloud. Then we're gonna also install the Torch Vision. Torch Vision is a plugin, I would say, of PyTorch that handles some computer vision libraries. In particular, DeepLab v3 is implemented in Torch Vision, which is the models that we're going to use. And TensorBoard is visualizers of training loss, validation loss, like basically a way to keep track of all the metrics of training neural networks. So this is the installation. So I would recommend you to install everything. Again, we are defining all different paths, where to look for the data, where to look for the weights now as well. We have pre-trained some models for DeepLab v3 and BAM-CD for you, because like this training can take hours. We don't have time to train for hours to have like a really good models. So we already have pre-trained some of them, and we have put the weights there. What do we mean when we talk about weights? Remember when we were talking about the parameters theta in our slide yesterday? Those are basically the parameters. And those are the weights. When we talk about architecture, we actually talk about how the neural networks, the shape of the neural network. The model corresponds to a trained algorithm on specific data, and the weights corresponds to the parameters of this architecture. So this is the terminology that is commonly used. Then we have the file for data sets, and whatever we're going to generate, we're going to keep the output on the part 5 of the folder CV4EO output. So first things, in Python you need to import all the libraries, all the libraries for satellite images, processing and deep learning, in particular like the H5PY, the Torch NN, Torch. So Torch is like the PyTorch things, like some data things, such as how to define a data set, a data loader, splitting functions. From Torch Visions, we're going to find some model of segmentation, such as DeepLab v3 based on ResNet 50. So it's one version of the DeepLab v3. We're going to see more into details how that is defined. And this is just the weight themselves, so the pre-trained weights of DeepLab v3 on generic sets for transfer learning. A fancy way to say I'm loading weights before fine-tuning on my own data, also called as transfer learning. I'm able to transfer a knowledge of something generic into your own case. And that's usually a way to fasten the training. Training from scratch is often difficult, as we said yesterday, because it might not converge. It is a lot to learn from, and you usually need large data sets. And transfer learning is basically means training on large data set that is very generic, sometimes in a self-supervised fashion, like one of the method, the mask autoencoders, like this encoder thinking. And the transfer learning means taking those weights, initialize my model with those weights, and continuing the training from that point instead of a random weights. It actually leads to way faster training. Then we're going to use PyTorch Lightning and some callback loggers and some utilities. PyTorch Lightning is a wrapper around PyTorch that fasten the development and the training of a neural network. And we're going to use torch metrics to have a binary F1 score that will be automatically estimated through that function. That's an overview of the imported Python library, but I think we're going to go through more details now. So the first things, if you remember the three pillars that we presented yesterday is when you talk about deep learning, we need the data, we need the architecture, and we need the model itself, and we need the evaluations. First here we are defining a data set. And in that specific data set, so we create a class in PyTorch that inherits from the class dataset that is imported here from the PyTorch library. So we have a class datasets and we are creating our own dataset. Now, differently from what we had before, we are not just reading the images of a very high resolution, so 1600 to 2000. We're actually going to create smaller patches of images of a different resolution, a smaller resolution. So smaller image would actually lead to maybe faster processing of those images. So we're actually going to reduce the size of the image. That would also reduce the amount of memory that's going to be used later on. But only for the sake of basically being able to train and run inference on this T4 GPU. So that dataset from PyTorch is usually defined by three main functions, which is the initialization, the length, and the get item, which are basically usually like dash dash underscore, sorry, for these functions. So the initialization is where you actually feed the data and tell him, look, these are the path of all my objects that I'm looking for. And whenever I construct the data set called the bird area dataset, I'm going to actually run a pre-initialization of all my data. And here in particular, my input would be an H5 files, the one that we have been using over the last hands-on. I define the patch size, the number of burned pixel that I want my image to contain. So I'm going to filter the region where I don't have any burned pixel, and an overlap, because basically I'm going to take my image and I'm going to create like many patch that overlap at 0.5 in that specific case to create many images from the same original satellite images. So in the initializations, I'm defining all those variables. And here as well, I'm also defining the band indices that I'm going to use to train that I'm actually going to use to create that new data set that I'm going to use to train my model. And here, as you might have noticed, actually, we actually don't use 3 channels. I'll give it a try by basically train with 4 channels. So it's something like just experimenting, and that's one of the strengths of deep learning. And you can actually create like some very customized data set and deep learning. And you might want to see, what if I had a 4th channels or a 5th channels to my neural network, and maybe learn some better linear combinations of those linear or non-linear combinations. Remember this activation between the layers of those different inputs. So here I'm basically creating all these patches. In particular, the first line is basically opening the H5 file. I'm looping over all the years contained in that file. So this is on 2017 we are working on. I'm looping over all the events, and I'm looking for the labels, finding the valid patches that contains a minimum of 50 pixels of burned area. Oops. My screen is not sharing anymore. It is still showing. All right, see the screen. All right, so I was basically here. I'm looking here at the valid patches, the one that contains at least 50 burned pixels, and I append all of these patches with information of the year, the event, and basically the X and the Y. What are the X and the Y? These are the patches, so the inputs and the labels. So the inputs defined by the band indices, right? No, actually, like all the bands actually still kept here, and the label separately. So the X and the Y's are basically returned here, and I just append them. So I create a number of valid patches from the maybe I think 70 or 100 events that happened in that specific year. Then the function length and getItem are the two other functions of a class called dataset that define my dataset in PyTorch again. That's going to be used to train my neural network. Length is basically telling me how many data do I have. So again, you remember like we had this concept of we have like a population of different inputs and we have a specific output we want to match that. Basically, we need to have a population of many samples, and in that specific cases, the length of the patches gives me the number of elements that compose my data set. And getItem is what I'm going to feed my my neural network in training to get the information of the input data and the labels that's going to be used in the training. So there's going to be like the looping from event after event that's going to be used in training. So in this stochastic gradient descent that Anthony presented yesterday, we're going to use these elements to optimize the parameters to converge towards a specific, the optimal value. And here I'm reading again the H5 file image. So I'm getting the patches. I'm reading that again. I'm getting the Sentinel-2 post and the Sentinel-2 patch in particular with a specific value of X, Y, and so on and so forth. Yeah, and basically at the end, I'm just getting the input data and the labels as on top of the year and the event. So this class is a typical class for datasets in PyTorch. In fact, that class inherits from the dataset in PyTorch and is customized for my need, which is the burn area with this H5 files that I'm actually reading. So now that I created that class, I can create an element of that class, which is my own dataset of an entity of a burn area dataset with a specific path, a size of the patch, mean burn area, mean burn pixel, and an overlap between the different images. Then, if I basically look at the elements of that entity datasets, I will have a total of 528 valid patches, and I can actually access them one after the other through the getItem. So if I take the element 0 of datasets, I will basically return the input data, the labels, the year and the event for the first batch of dimension 256 by 256. Now, I don't know if you remember, but we said that most of the optimizers don't optimize image after image or the whole data set at the same time. We are using some algorithm called stochastic gradient descent. And the stochastic gradient descent is actually a batch-based optimization that does not take a single image or all the images together to optimize the weight. It actually takes a batch size, a specific batch of a specific size that basically optimize the weight of my parameters of my model to reduce like its loss. So for that, we actually create a data loader. A data loader will take my data set and combine that into batches, in particular of size 2, which means that I'm going to use 2 batches at every iteration of stochastic gradient descent to optimize my parameters. And by iterating over that loader, I'm actually getting the images, the labels that are defined from here, as well as the year and the events that are actually not storing in any way. So when I run that part, first of all, there's an info from PyTorch Lightning that tells me that he had found 529 valid patches. It's actually the log And if I print further later some informations, I can see that I have a total of my loaders of 265 batches of 2 patches. Okay, and each of my batch has a size that is contained, that has that shape here, a size of 2, which represent the size of my batch. So I have 2 tiles, 2 images of dimension 4 channels, which are the 4 channels that I have defined, and a resolution of 256 times 256. And for those images, I have the exact equivalent label. So basically, it's a way for me to process the data sets and make it in a suitable format for my algorithm to learn. So I basically patchify my big image of 256 by 256. I extract the 4 channels, and I batchify those patches. Sorry, the B and P is a bit tricky. Fun fact, in the Arabic language, by the way, P and B is the same letter, so I should not be able to give that that things in Saudi. But basically, we have in total 265 batches of 2 patches of images. Any questions so far? Good. Okay, just like pre-processing the things. So let's look at what it looks like. So yeah, that's what I think. That for size 2, 4, 256, 256, 2 represent the batch size, the number of images in the batch. 4 is the number of spectral bands, and 256 times 256 are the spatial dimensions matching the size of the input patches. Now, let's look at what those images look like. For that, I'm going to use matplotlib, get some samples from the loader. I got the image, the label, the years, and the events. You might have noticed that this is plural. Why is that plural? Because we have a batch of 2. Here, I'm actually extracting the near band and the labels in particular. So the near is actually the first element of my image I, for I being from 1 to 2, because we have 2 images. And for the 2 images, I'm actually plotting their value. So here, the first I is range of 2 because we have 2 images in the patch, and the second one is because the first image is actually the near patch and the one's the label patch. So basically, it's a way to clean our data. Here, we have the near patch 1, which actually identify a very small area of fire here, that of burn area, that is actually here. And we have another patch of 256 by 256, where we have a small area here. Again, I set like the value to 50, so we want to have at least 50 pixels that actually contain the fire. So all of our images should contain fire. If we put that to a larger value, we might have like regions that are bigger, but the problem is that we might have less data. Right now in that event, I have 520 something patches. If I only filter the one that are actually quite large, I might have less data. Because I have less data, I have less diversity in what I want to train on. So again, the more data, the better. Okay. All right. So we've created the data set. There is an extra part for that, which is the wrapper from PyTorch Lightning. This is not something that is necessary, to be fully honest with you, for a training, but it's an extra library that makes it even simpler to train your neural network. It's a wrapper on top of PyTorch that define all the different steps that is required for training on that specific data set. So we are going to use that library right now.
If I may complement something also, if you're missing some parts, PyTorch Lightning would tell you that you forgot to implement some steps, which is very nice compared to just using PyTorch Basic. So it's also a good way to check that you implemented everything that is needed to train a network.
Exactly, right. So the PyTorch Lightning is a wrapper that goes on top of that, that I can create later on an entity for that. And it actually goes one step further. You create inside that setup, basically, your burn area dataset that is based on the H5 file that we've been set. And then we define what's the size of the training, the validation, and the test size. And in that specific case, you want 70% of the images to use for the training, 15 for the validations, and the last 15% for the test size. And you can do a random split between, for that specific data set, between train, validation, and test, and use a generator that has been seeded to a specific value just to enforce the reproducibility. As you can see, there is like a random split, which basically means I might split the data completely randomly, which means that if I split in a specific way and to split it in a specific way, we might actually get some different results. So just for full reproducibility, I'm seeding that, so it's still random, but the randomness is the same for everyone. So you can train multiple times and you always get the same results. And then you have the functions of basically how to create data sets that are functions that come from the PyTorch Lightning. You can train, you have the train data loaders, the validation data loaders, and the test data loaders that are created from those different train data set, val data set, and test data set. Okay? All right.
Maybe if I can complement just with a bit of theoretical understanding here of why this seeding is important to reproduce results. So when we are training using stochastic gradient descent, so using batches, if you remember, what we're going to do is that we're going to take a step that is based on the gradients of 10 images out of our entire dataset, or in this case, just 2 of them. If we choose different, even if Silvio and I choose the same initialization point, let's say right here in this 3D space that is the room, we select the same point. If we use different batches, then we might end up in different points after a first iteration. And then when I'm going to upload a new batch, my gradient will be different because my initial parameters are at different spots. And so actually there is the convergence might go differently depending on the order that you present the images to the network.
Yeah, and training is a stochastic process, and my train actually leads to different results every time you actually train. Mm-hmm. That's why seeding is extremely important, because you always get the same result. Of course, you can try multiple seeds to see what the model actually works best. There is a concept of hyperparameter search, where actually you launch maybe hundreds of training in parallel, and they all converge to different places, and you can, usually they reach like more or less the same performances, but there is a little bit of stochasticity in that. So instead of having like some performances that might reach like 80%, you might have 80.5 or 79.5 performances. That's why it's important to sometimes have some, it's important to know that there is a stochastic process. It's a stochastic process.
Also, when reporting results, usually what we try to do is not report the results of one single model trained, because it might be that you are just cherry picking the seed, which makes no sense to compare different methods. The way we usually do that is by averaging the performance of the different models. So we run 10 different models, or 20 or 30 with different seeds, and then we say, all right, on average, we get this performance plus or minus some variance. And this should be the standard way to compare models. This is not how it's done every time in practice. Sometimes for technical reasons, because if it takes 2 weeks to train a model on 200 GPUs, it may not be possible to simply try out different seeds. But yeah, it's a good practice to run it on different seeds and average, right, so that you get an idea.
Exactly. So here with that data loader, that data module from PyTorch Lightning, I can create a data module. So I can set up that data module that basically create the data loaders for training, validation, and test. And I can define like some sample for training, for validation, from testing. And if I just sample one of them, the batch size in that specific case, I actually notice that here the batch size has been set to 8 for that specific loaders instead of 2 before, which basically means that if you log those things, again, the dataset tells me I found 259 valid patches, because my patch size is actually 256, and I choose like an overlap of, a minimum size of 50 pixels. I have a number of training samples that are 370 for training, 79 for validations, and 80 for testing. And those are being batchified, and there have been a batch of 8 for the remaining, 4 channels, and the resolution of 256 times 256. Here, there is somehow like no visualization. That's why it's very difficult to actually visualize something of 4 dimension. In 3 dimension, when you have RGB and the dimension, you can actually represent that as like colorful images where specific channels represent specific red, green, or blue channels. But when we are in deep learning, actually, we most often like plot the shape of a tensor, because this is how we understand what our data look like. And it's less about the value itself rather than the shape of what it looks like, because we know we're going to optimize that, or we know it's an input, so it has that shape, so that we're going to be fed into our neural network, and we're going to learn something. So use that visual concept as we had in the previous 4 parts, where we actually visualize what the different channels look like, save them in GeoTIFF, and so on and so forth. This is raw matrices of data, tensors actually, because they're higher dimension. And we often like just visualize them by just identifying what they look like in terms of shapes rather than what they look like in images. All right, so that's our data, and that's our data loader that we have created with PyTorch Lightning. Now let's go to the next step, which is the model architecture. First, maybe do you have any questions about the data itself? Basically, creating patches, 4 channels. We decide the channels as an input, and then we create, we batchify them, 8 of them that we're going to feed to our neural network step after step, iteration after iterations in our stochastic gradient descent algorithm.
We are still using the Sentinel-2 image.
Yes.
Of the 60 meters of 2017.
Yeah. Yes.
So the whole batch. Yeah, sorry for that.
The whole data
of that year.
Yes.
And there is where we are looking for the batch.
Yes. Exactly. So if I go back to the very beginning of what we actually had, no, it's fine, because actually we're going like so deep into like pre-processing those data. It's actually important to actually look at that. But the original files is actually what's actually shown here. We're talking about Sentinel-2, 60 meters. Those contain the bodies 500 meters of the FlowGAT datasets from 2017 from Sentinel-2, 60 meters for Sentinel-2 and 50 meters for MODIS. So we are only using 1 year. 1 year of that dataset.
It has how many images inside?
I forgot. I think we need to go back to the first one. And when we were in the H5 processor and we're looking for that, those are all the events. So the indexes goes up to 86. So but some of the indexes are actually missing. Like there's no 81 for some reason.
It looks like for 20, around 15 to 20. I think.
15 to 20? No, a bit more, I think.
Maybe a bit more.
I think there were like 60 events or something like this, 60 or 70 events that happens in that specific year. Here I'm only talking about the 2017. I could actually do the same with the concatenations of 17, 2018, 2019, 2020 that basically contains even more information. But just for the sake of that specific workshop, I only took 2017. In fact, the more data you actually gonna feed, the better the performance is, because you actually learn from more information here.
But the longer the training. That's basically the drawback.
Yeah, I'm thinking also of the vegetation on the different seasons, the seasonality of the vegetation. So maybe it's better to consider different years, but the same.
That's
season.
very true. Yes. Yeah. For AI practitioners, it's like more data the better. The more diverse, the better. But what diversity means, this is something that domain experts could actually help us identify. Maybe there is enough diversity in a year because there are 4 seasons, but if there are like I don't know, different vegetation from year to year, maybe it makes more sense to actually also look at 2018, 19, 20, 21 and more diversity in time. But that becomes more like a case by case kind of study. Of course, the more diversity, the better.
But in this case, it's interesting to have the full year and the seasonality, because on the method of the NBR, I've seen the product where they mapped the burnt area in Canada in the winter on the snow.
Okay.
So that's very important to learn about the full seasonality, to see those cases where you know about.
Diversity is really important, yes. And often with data augmentations, this step of artificially augmenting the data, it's quite common to see, I've seen, for instance, in autonomous navigation, when you have data of autonomous car trying to navigate that have been trained, for instance, on summertime, they artificially change what it looks like to look like it was raining or snowing, just by generating new images of the same land, just to augment the data sets and artificially create some use cases or some data that to train on that covers those the specific case that you mentioned. Enforcing diversity. Again, we want to enforce as much diversity, but the diversity is a concept that is relative to the domain of applications the domain of application. But yeah, so Floga 2017 Sentinel-2 data.
Or pre-post.
Here we have both the pre and the post. So we are provide.
But the patches are only.
I think we only take the post here. Sorry, here we're only taking the post because we are talking about the neural network that is only taking one image as an input. It's not yet the BAM CD that we showed yesterday. This is just like a deep neural network based on convolutional neural network that takes one image as an input and one output. So here, in fact, when you look at the get item of the data set, that is basically here, when I'm providing the input data and the patch data, the input data is a stack of like some selected bands from the Sentinel-2 patches that come from the Sentinel-2 post. So it's the post fire only. So when I talk about the input data here, the X, I'm only talking about the post fire. I'm not considering the pre-fire yet.
No, otherwise you don't find the 50 pixels.
But the 50 are actually extracted from the labels itself. So, oh snap. Okay. Well, I'll have to run that again.
Yeah.
Great. But yeah, basically from the label itself. Good. Okay, so proceeding now. I've been disconnected, so I think my training that I was running has stopped. I'm just going to check what happened real quick. Okay, it's fine. I can still run everything. Just want to check that I have access to that. Oh, snap. I'll have to run it again. Okay. All right. So I had to run it again. I hope it won't take too long. Perfect. So I stopped. Where did I stop? Sorry, I had to run again the code. I went here. Takes some time to run, sorry. Training for this one? Yeah. Oh, it's just training for you. Okay. Okay, so here I created the data set. Here I'm plotting again the near batch and the label batch for the two elements of my batch. Here I created the PyTorch Lightning data module. I'm initializing that. I get the 529 valid patches, the train 370, the validation 79, and the testing sample 80. And now we are creating the model architecture. So first pillars is basically data sets. How we clean our data to be fed to our black box neural network that will be trained on this data. So in particular, we are going to adapt the DeepLab v3 models with a ResNet backbone encoder. Remember yesterday we talked about the encoders that basically can be transferred from one task to another. This DeepLab v3, so semantic segmentations, which encoder is actually a ResNet 50 pre-trained on some other task of classifications. And the DeepLab v3 is just a special head that will create a semantic mask out of that. Then we're going to yes, actually, transfer learning, retaining knowledge from the pre-train while adjusting the first layer. We'll have to adapt actually DeepLab v3 because the ResNet 50, the backbone encoders, expect only 3 channels as an input, which is actually not what we have right now. We actually have 4 input of channel because we are in a multispectral case. We don't have just RGB, we have 4 channels. So So we're going to adapt that from the standard 3 bands RGBs to the 4 bands that we have decided. So we need to actually change and tweak a little bit our model architecture. And then we're going to use the cross entropy loss and the F1 score as an evaluation matrix that we're going to monitor with PyTorch Lightning. So, all right, the PyTorch Lightning provides modules to create models. Like this is my burn area models that I want to train, I want to initialize, and I want to define what is the forward step, I want to show what's the training step, what's the validation step, what's the test step, and then different optimizers that are needed. So let's start with the initializations. I want to define my models. So what do I need to know from my models? I want to understand what type of input it actually can accommodate for and what type of output it can create. And in particular, the output of my models is defined by the number of classes. So what we're going to have is a specific number of classes that we are showing here. We're going to initialize our PyTorch Lightning models, have some specific hyperparameters, a specific learning rate to start with. We can actually tweak that hyperparameters. Yesterday, we defined that learning rate as how much I'm actually moving towards the direction of the better parameters or better weights of my neural network. This learning rate has been initialized to 110 to the power of -4. I'm initializing my model here with that specific number of classes. I'm defining a criterion, which is a loss that I want to minimize. So that loss is how much mistake, how far away I am from the optimal sets of parameters. And then I'm defining training, validation, and test F1 scores for each of these datasets. Initialize the models means creating a DeepLab v3 ResNet 550 entity that has been pre-trained with the weights that come from DeepLab v3 ResNet 50 weights by default. So basically that means here I'm creating the models. I don't go too much into the details of what that models look like. It's a bunch of CNNs. It's quite heavy as well. And the weights has been pre-trained already, and we just like load those weights and we initialize the weights of my models to be from the default one already pre-trained. But we'll have to do some modifications, and in particular, our models contains a backbone. A backbone is an encoder, and the first convolutions that originally accept only 3 channels. So the first layer of my neural network, I don't know if you remember, if you have like specific layers, it only has 3 input, which is the meant for RGB, but we actually input that with 4 channels. So how do we change the convolutions, that specific model of the convolutions, to accommodate for 4 of them? Here, the way we did that is by overwriting the model backbone first convolutions to PyTorch 2D convolutions that accept as an input 4 channels rather than 3 channels. And it goes from a dimension of 4 to 64. This is one of the design choice of DeepLab v3. Originally it went from dimension 3 to dimension 64, but we changed that to dimension 4 as an input because we have 4 channels. If you would like to use the 11 channels of 12 channels of Sentinel-2, you could actually change that number from 4 to 11. So you can actually run a linear combination of all the channels of Sentinels to actually even have more parameters and more. Of course, the more channels, the more parameters needs to be fine-tuned, because here we're actually increasing for that specific layers the number of parameters by 33%, because before we had 3 channels, now we have a 4th channel. In fact, there is one thing that is quite important. It's originally that convolution layers actually have some pre-trained weights that was loaded here, but it was meant for 3 channels only. How do we leverage still like this pre-train? It's extremely important to do this transfer learning from pre-trained models to the downstream task for fine-tuning it. With that layers, we're actually saying, with those 2 lines of comments, that now I need to initialize like 4 dimensions. The first 3 dimensions are exactly the dimension of the original convolution layers. And I add a 4th initialization that in that specific case, I decide to be the mean value of the three channels just at the fourth channel. That is not an optimal way necessarily to optimize, to initialize my weights, but it's a better than random, basically. So it actually will help converging in general. And the last thing I need to also modify from my models when I initialize is the last layer of my neural networks tell me the number of, is defined by the number of classes that I actually want to classify. At the end, I have 2 or 3 or 4 classifiers that tells me if it's class A, B, C, D. In that case, we only have 2 classes, burned or non-burned. So we have 2 classes. So we are changing the last layer of the classifiers to be a convolution layers of dimension 2, because we want to eventually learn it's burned or it's not a burned area. Great. That's maybe like the most important part to basically understand the model itself. We started with a convolution neural networks pre-trained, but we modified the architecture. You can imagine like a surgeon somehow that will open the different layers and try to change some of the modules to accommodate for the input and the output of the data that you have in hands right now. So if you would have more than 4 channels as an input, you would change that parameters to the number of inputs, and a way also to initialize the missing weights for that for those new channels. And for the output, the number of classes is defined by the output of the last convolutional layers of the classifier. Good. So then we define some forward steps, which is basically feeding like the model itself. When I have an input X, I want to define what's the output, and it's defined by that line of code for that specific model. And then I have some shared steps that I think is basically for a training step, a validation step, and a test step, which is basically when I receive a batch of data. So I've defined like a training data set, a validation data set, and a test data set. Every time I receive a batch of patches for the training, validation, and test, I need to do some operations. And these operations are defined through the shared step here, which is basically taking my batch, extracting the images and the labels, taking the self of the images, taking the images themselves and processing them with the model that has been defined through the forward step here, getting my output. So this is the predictions directly. Then I take my criterion, which is my loss. It's like this difference metric that I have between my output and my labels, and I create a loss. Basically, a single value that will tell me how far I am from the optimal ground truth, from the optimal labels. And I want to minimize that loss. And I also have a list of predictions, which is defined as the argmax of the output. Remember, the outputs are basically a dimension of the number of outputs, like in that case 2, which are confidence score of it to be either of class burned or unburned pixels. And the argmax will tell me the index of whether it is more of a value of burned or unburned. So it gave me the information of whether it's class 0 or 1. This is the prediction. And then I automatically estimate the F1 metrics, and I run the F1 metrics for the predictions and the labels. That's just a trick to basically take the stage, and basically this is the F1 metric for train, validation, and test. And I take my predictions, I take my labels, I run the F1 metrics between the predictions and the labels, and I get this F1 score. Eventually what I'm having is I'm logging the information for the loss that I've estimated here, and the F1 score that I've estimated here. And I'm logging the information as I'm actually computing the stochastic gradient descent, batch after batches after batches after batches. Okay? All right. And yes, I forgot to mention, and actually that's tricky, we also configure the optimizer. Here, without going too much into the details, the optimizer I'm using here is not exactly stochastic gradient descent. I could have used stochastic gradient descent, but I'm using an ADAM. It's a slightly optimized stochastic gradient descent, but the idea is exactly the same. I'm taking a batch, I'm estimating which direction I go, I define the learning rates, how fast I go toward that directions, and I'm optimizing the parameters to go towards that directions, what that speed somehow. This is the learning rate that is defined here. Great. All right, here I've just defined the models. I have not started training anything. So a lot of, I hope you still bear with me, sorry about that. But basically here now I can initialize, now most of the things are actually done. I've defined my data set, I've defined my model. I can initialize my model now, the number of classes, the learning rates, run that in evaluation mode, for instance, and print the output of that shape. So here I got for my prediction, my output directly of my specific models that indicates the 2D segmentation map for each image in that batch. It has two values for each class, the burned and the unburned, and the argmax actually tells the information of which one is the most confident. Is my model more confident that it's burned or unburned? That's what the role of the argmax. But let's go directly to the next step. The training actually just happens here. 5 lines of code, and you can actually now train a neural network. So here in my trainers, I'm taking the trainer of PyTorch Lightning. I'm defining the number of epochs, which accelerator I'm using, how many devices I have access to, and I have a bunch of callbacks that just like save checkpoints my model from time to time. And then I just take my model, my data modules, and I'm just running my training to fit the model, the parameters of the models for my data module. And the data is basically the training, test, validations are actually computed on the fly. So that is the part that actually has been running for the last 10 minutes. And it took me actually 20 minutes between all these times to actually train. It takes on average like 20 minutes to train for one epoch. But basically this tells me the information of, first of all, what hardware I'm actually training on. I have access to GPU, the T4 that is mentioned here. I'm not using any TPU nor HPU. I have to admit that I don't know what an HPU is. It's something that's changing every time. I'm using 529 valid patches. I'm using the CUDA library on the GPU of index 0. And I'm plotting some information about number of parameters of all my different modules. So I have some scores that do not contain any parameters. I have a criterion, which is my loss I'm actually trying to optimize, which is a cross entropy loss. And I have a model that is a total of 42 million parameters that I'm currently training right now. Like here in the epoch, because I have a training batch of 47, which is basically means like if I combine all my training data and I put them in batches, I have 47 of them. And it took so far 9 minutes and 19 seconds to actually train for 10 epochs. It's only refreshing any 10 epochs for the visualization. And I can plot my train loss and the F1 score so far, which is still equal to 0 at that specific steps. And it still requires another 12 minutes to finish training. Okay, it takes a lot of time, it takes a lot of epochs, and in fact here I will only train for a maximum number of epochs equal to 2, and I'm training on the GPU on one device in particular. Training like to get like better results, it takes way more time, so this is just a training that can span 20 minutes, but I think I'm going to stop it here to just proceed in that part. Yeah, so basically here's me training the algorithms. It can take like a couple of hours, so I'm just gonna stop that part right now, just for the sake of moving on. Okay. Any questions so far?
Yeah, I ran it. It's finished with the epoch 0, and now it's gone on to the validation. But it will take a long time as well for the validation.
Right. Yeah, validation is a bit faster, but after epoch 0, it will go to epoch 1, then epoch 2. So it might actually take a bit further. But the validation steps, you might see the validations. It might actually print some value for F1 score or the loss itself. That basically being decreasing. But good thing for you is that I've already created some logs that we're gonna explore right now. So I've trained for 50 epochs, and I've logged everything in TensorBoard. TensorBoard is a tool that has been developed by Google through TensorFlow that also runs with PyTorch, and it's a really nice user interface to log all the information that you're actually doing. Here, you see like the number of epochs that we have run so far, so a lot of options here and there, but basically here I keep track of the F1, the loss, for the training, and the test and the validation, and I can see what it looks like. So here I have, can I do something like this, right? So this is my training loss over 600 steps. 600 steps means 600 iterations. Does not necessarily mean epoch, because we had well, I forgot if it's that actually 600 epochs. Actually, Virgil, if you hear me, maybe you can write on the chat if this is like 600 epochs or actually only 50 epochs. But basically, you can see that the loss is decreasing until like some more or less convergence. So that's the train loss that basically we are optimizing. We are basically going down the mountains, finding like the directions, the gradients of where to go down, and we are taking some steps to minimize that loss. So it's 50 epochs, okay. So that's basically the steps of how much iteration it has actually done. And basically the loss is decreasing. Doesn't mean that the lower the training loss, the better, because we might go to overfitting. So looking at the validation loss, here you can see that it's not necessarily very smooth, first of all, but the validation loss is decreasing. At some points it's sometimes increasing, but in general it's still decreasing, which means that you still have room for improvements. There's a few tricks that exist in the literature to understand when to stop training, for instance. One of them is identify over the last couple of epochs whether you have actually a better validation loss in some epochs. So if you can consider like for 10 epochs, you're actually not decreasing the validation loss, you might think, okay, I have actually converged right now. Of course, the more you train, the longer it actually takes. So if you are satisfied with these performances, let's say, you can actually stop training here. In fact, if I look at the validation F1 here that I plot, if I only want to have the F1 to be above, let's say, that value 75, if I just want 75, I can actually say, okay, I have an F1 score that is good enough, I'll stop my training here, for instance. Okay. All right, but I can see it's still like improving the F1 loss. Again, the F1 loss, the better, the higher the better. The training loss, the lower the better. So that's like a training that happened that we have trained before for you to see the different logs, how that goes. And for the test, we don't have the curve, of course, because we are only expect to test once. So we don't look at the test iteration after iteration after iteration because we might overfit on the test set. So for the test, only at the end, we see that we have a value of 70.5% F1 score on the test set. Okay. All right. Another step is the inference step. Once you have trained a model, in that case, we haven't trained it fully. So I'm actually looking for a checkpoint here that I've pre-trained before. The DeepLab V3 had the best performances at epoch 48 in particular for a specific validation loss. So this is the checkpoint of my weights. So this is a heavy file, maybe like 500 megabytes of 43 million parameters that I've stored in my Google Drive. And I can just like read right now, and I will load that specific checkpoint. So here I'm taking my burn area models and I'm loading from the checkpoints, which is that path in particular, and I will put that on the CUDA GPU because I have access to a GPU here. Here I'm basically taking the data with the same batch size and the patch size. I'm creating that data modules. I'm setting that up. I'm taking the next iterations and I'm going to predict on the image the models, and I'm taking the argmax, which is basically the predictions of whether it's class 0 and 1. And then with that, I should be able to get my predictions, my labels, and my images on the CPU. And from that's actually loading for one of the image, or actually for all of the images. Sorry, I can calculate some of the metrics that we defined before, in particular the true positive, false negative. Here we define the F1 score as the precision recall in that formula. And if I run that, I think it's still running the inference on the test set.
So if they want to see, if they want to follow along and not go to training the whole model, they can just stop the training right?
I stopped it, yes. Yeah, sorry, I forgot to mention that, but I also stopped it, right? I showed you that here. I decided to stop it after 13 minutes, was not enough for me to train, but you can stop the training and
jump back.
And jump to the rest, because the rest of the code is just preloading the model that I've trained already.
To stop it, how do we do that?
There is a button play here. If it's running, you can just stop it by hitting the button stop.
It takes a bit of time to stop as well, so don't be surprised.
Yeah, done.
Exactly. So here I calculate some metrics, and then I'm running that cells, which is basically looping over the images and plotting some performances. And here you have the output on the test set of what the image in the near infrared band actually look like, what the ground truth look like, and what the model has predicted. And that's pretty accurate. It's pretty accurate. It's not perfect. Like if you look at what the ground truth look like, you can see that it's a bit, the details is actually a bit crisper, like more details. Here's a bit more smooth. Another example is here. This is what I was expecting as a ground truth. I actually had something that is a bit more smooth. Again, that's a deep lab V3 model that only take the post-fire. We have not taken the pre-fire at all. That's another example. Ground truth looks like this. I was expecting something else. Some other metrics that I'm actually showing is like the ratio of the burn area. Like sometimes you're not that interested in like how much, where it is, but sometimes just like what's the proportion of that area that's actually burned. We just like display that 0.22% versus 0.27%. Same here. Here we actually have missed a part of it. And those are all the results for all the test images. All right. So the model shows some spatial accuracy, and we have an F1 score of 91.88. I think it's shown somewhere. It's like, I think the average has been calculated somewhere. But it struggles in some cases, in particular the image 7. Image 7, which is this one here, for instance, he actually has not detected anything. So I have 0% here. I don't detect anything. So the F1 score in that specific case is equal to 0. Here on top, I have an F1 score of 72 for that specific region. Here I have a F1 score of 25, which is actually quite low. Here, actually, that's another use case where it actually has failed, more or less. But in most of the case, it finds some regions of interest. Okay. All right. I think I went very detailed into that part. It took a bit more time than expected, but I think that was the part that regards the deep learning, right? So that was the part that was, I think, maybe the most important for that hands-on is basically how do we define data sets, how do we find models, and how do we train models on the data set, and then evaluate its performances.
And it made a good link between what we've seen yesterday from a theoretical perspective and how it is actually implemented in PyTorch.
Right, exactly. Good.
Can you remind me again what computing power we're using here for this training, for example?
It's a GPU called the T4 GPUs, which has 16 gigabytes of RAM. So if you go to this little triangle here and you go to view resources, it actually gives you some information about what you're actually using. The T4 GPU has a GPU RAM of 15 gigabytes of RAM, and some CUDA core for that. I think for the BAM CD, I will go really quickly because I think I would like to go to the sixth part, which actually took the GeoSAM, and we only have 20 minutes left, right?
A little bit more.
A little bit more, okay,
We have
perfect.
an hour and 15 minutes.
Oh, we have an hour and 15 minutes? Ah, to 1:30, okay, we have a lot of time.
Unless you want to shorten
Right.
but you have time.
Okay, good. Okay. Do you have any questions so far? Did that answer most of the question of how to use deep learning in practice with Python and PyTorch?
The advantage is also that here, since we are loading the DeepLab v3 model from the Torch Vision, it also means that if you want to change the model, it's actually 1 or 2 lines to just change if you want to test out another model. So you can really use that as a template almost if you want to change the dataset, if you want to change the model, if you want to change the number of classes, everything is inside this, so you can come back to this this notebook as well at the later stage.
So maybe I will just like spend 10 minutes for the rest of this notebook and then move to the next one. Basically, the remaining of that notebook, we're only actually halfway through it, but it's basically the definition of the BAM CD models, the one that is actually implemented in the Floga paper. So there is some explanation about that models. So remember what it looks like, that models, it looks like this, right? So it's this architecture where I have pre-fire image, post-fire image. I combine them into some residual convolution neural network blocks together, and then I decode them into the final binary mask of burned and unburned. Okay, so moving on, basically, what is the main difference that we have here? First of all, instead of just loading GitLab v3, we now need to create our own models. And for that, I defined a residual block that is one of the building block of BAM CD. It's composed of convolutional neural network, some batch normalizations, a second convolutions, a batch norm, and more and more convolutionals and batch norm, and then some ReLU for the activations, and the 4th step. So the way I define a module in PyTorch is that I initialize some weights, so some of my learnable block in my initializations, and then I define what is the 4th step. How do I take my input X and I place them to, I process them step by step. And here in particular, if I take my value X, I have the residual skip connections that is used later on. Then you actually have the first convolutions, you take the output, you place it, feed it through a batch normalization, then you put that output into the ReLU activations. We haven't went through what a batch normalization look like, it's just a way to it's a reduce overfitting, I think.
Yes.
And the second processing block, it's a bit of lighter versions of what we have, just to, for the sake of training, because I think there is like 5 layers here, or 4, we only have 2 in here. Then we have the identity. Oh, that's not, sorry, that's only for the residual block, so it's normal. There's only like convolution, batch mode, convolution, batch mode, and the skip connection. Then we define what the convolutional blocks look like, which is the convolution, batch mode, ReLU, with the forward, which is basically, I take my input, I pass it through the convolutions, the batch norm, and the ReLU activation. Those are the 2 building blocks that are needed for BAM CD. BAM CD is also initialized, also PyTorch modules that take as an input 4 channels. It's defined by convolutionals for the pre and the post, one convolution for the pre-fires and one convolution for the post-fire. It's a 2D convolution that takes as input 4 channels in that case, and project that into a space of 64 dimension. It has also some max pooling, and then it has a few residual block residual blocks for the pre-fires and for the post-fires, some convolutional blocks that goes back for the decoder part, And then a final convolutions that has an output of dimension 2, which is the burn and unburn layers. The fourth step looks like this. If I was a pre and a post image, in that case, you can see that the fourth step now does not take only one X as an input. It has two X. It has the X of the pre-fires and the X of the post-fire. So in that fourth step, it would actually expect two inputs, the inputs from the pre-fires and the inputs from the post-fire. It will run some convolutions for the pre-fires and the max pool of the pre-fires, and same thing with the post-fire. And then it states again that this is like how it goes. So it takes like the residual one that has been defined there. It takes the pre one, same thing for the post. So basically those things are the 1, 2, 3, 4 layers that actually defined here. 1, 2, 3, 4 for the pre-fire, 1, 2, 3, 4 for the post-fire. And then it aggregates all the different information. So it concatenates the pre-fire and post-fires at the fourth layer, and then it redecodes that, and you have a final convolution of layers that has a size of an output of batch size 2, the 2 channels for the binary classifications, and the height and the width that's expected. So see, it's like here, it's a bit more complicated because you actually define your own model itself, built with multiple blocks. And you can define any models like this. And this is the strength of the PyTorch library because there's a lot of things happening under the hood. For instance, I told you like for optimizing the parameters, you need to backpropagate the errors of the loss through the derivative of all the different parameters that goes back in times. So you need to define 4 steps of what does your inputs is mapped into an output, but also what the variation of the outputs would actually lead as for a variation of the parameters. So you need to define the derivative of that. So this is a backward step that needs to be computed, which is our complicated derivatives that is defined for every single layers. And when we talk about yesterday we talked about like the modules that are actually here needs to be differentiables. By differentiable, it means that every single module that has been defined in here, the res block or the convolutional blocks that are modules from PyTorch, they are fully differentiable, which means that when there is an operation that goes in the forward, so going from input to output, they also define the backwards, so the derivative. So if I have an error at the output, how much should I change my parameters at the input? So you have a lot of backward chains that basically optimize all the parameters that is being taken care of by PyTorch. So it makes everything very easy. You only define your forward, once your input becomes how your input is transformed into your output. And if you have an error at the output, at the optimization step from SGD or ADAM for this optimization step, it will change the parameters of all those building blocks without you having to derive like very complicated derivatives. Yeah, so good. So that's basically defining the band CD module. Actually, let's run those things because I think I haven't run them yet. I'm defining the class residual block and the BAM CD here as well. So I'm defining those 2 classes. Now, here I can again define, oh yeah, the dataset also needs to change in that specific case because the data loaders does not contain only the post-fire now. You also need to feed the pre-fire. So this is like an updated of the burn area dataset that I've created before. But now when I get the item at the end, I don't only get the item of the post patch, but also get the pre-patch. So here, instead of defining only the post-fire of Sentinel-2, I'm also defining the pre-fire, and I create the patches for the pre and the post-fire. And I return the pre-patch, the post-patch, and the labels, as well as the years and the events. So let's run that as well. I define the data set. I've been disconnected. Are there any questions in the meantime, or is everything clear actually? It's a bit too, they're going a bit fast. Okay, I'm back. So I'm back here, and here, as I mentioned, so the burn area, so once I define like my data sets, I need to again to define my Lightning data module that creates the training set, the validation set, and the testing set. And I'm running that part as well. It's exactly the same thing as before. And the Lightning module also for the model itself, for the training itself, where I define my model here with the input channels, what the forwards look like. Now I take my models and I feed it not with only with X, but also with X pre-fires and X post-fire. And I have a training step, validation step, test step, and I use the same optimizer as before, running that part. Here I won't be able actually to train it because that models actually has been defined in the papers, needs to be trained on larger data set, on larger, sorry, it's quite heavy and actually needs to be trained on 4 GPUs. So I won't be able actually to train it, but I will show you how it looks like. So if I want to set up the training, I define my models, I define my burn area data module with a batch size of 8. Then I create some callbacks for the checkpointing of different values. I have some TensorBoard logger to log some informations. And then when I train, I should train that for 50 epochs on the GPUs on 4 devices. Unfortunately, that 4 devices doesn't work here. And then I just run the trainer that fits models, that fits the model with the data module, and then I can just get my results. But that can only be trained internally. So that Jupyter notebook, if you'd like, you can actually download it on the workstations or on your computers. If it has 4 GPUs, we managed to train it on 4 RTX 20 Ti's GPUs that we have access in our university. And then I have the logs for you for that. So we won't be able to train, but I still have access to the logs of that training. And the F1 score typically should be slightly better. So I have trained for 50 epochs. If I look at the training loss, it's decreasing, not always, but sometimes you see it's very noisy, kind of. The validation loss is also like this. There's also like some very high noise that happens here at some points. I think it might be due to there's a specific scheduler in the learning rates that basically reduce the speed on which I'm actually optimizing at the very end. But that's just an engineering trick that leads to some results like this. But eventually the best performance for the test set managed to reach a value of 84.57 compared to the 70 point something before. Which means that here with that model, we have a performance of 84.57 in the metric F1 score. That is almost aligned, I think, with the tables that I've shared before. Here is, I don't know if you can see that, but if we look at the F1 score, we're talking about that F1 score here, about the burn pixels. This is the indexes. This is the machine learning algorithms. These are other deep learning algorithms, and they were managed to actually reach 88.48. We only get 85, but we only train for 50 epochs as well. And we actually only train on 1 year as well, 2017. We actually train on the 6 years, which basically could provide more information that leads to even better performances. Right. Great. Are there any questions? All right. The last part is basically once you have trained the models, we have trained one for you. You can get the checkpoints here. We also have like written like and hard coded like the test batch path in that specific file, and you can with those lines of code load the models and the batches and make some predictions, compute some metrics for specific images, and plot all the results of the pre-images and post images. Let me see if that works. I think it's here. So here I'm loading the models that I already trained, the batches for the test set. I'm getting the batches So this is what the pre-fires near-infrared look like, the post-fire near-infrared look like, the difference between the near of them. And as you can see, the near-infrared can actually already highlight some regions. In fact, the ground truth is actually here. And the prediction is a bit crisper now. There is like more details. It's less smooth as Deep Lab V3. Because now, because you have access to the difference of before the fires and after the fire, you have more information, you feed more information to your neural network, to your architecture to have crisper details. It's still not perfect. In that specific example that we also highlight, we can see that sometimes it hallucinates some data, where it hallucinated the fact that there is some region here. Voilà. So that's it for that. There is some hands-on exercise if you want to play around. This is basically you can apply some other predictions here, and I would invite you to look at that maybe offline. And if you have any questions, I'm very happy to help you with this. Okay. Are there any questions about the deep learning? Was it clear enough? Are you confused? Is it like too much material? Was I too fast? I don't know. Like, happy to have any of your feedback to that and clarify any doubts that you might have from these hands-on sessions on how to train deep learning algorithms on custom data.
Okay, that's super interesting. If I could do the same based on other data sets, water, and even operationally, if we have a data set with a building that has been destroyed by an earthquake, we can feed that and then run that. That would be possible.
Absolutely. The data you need is basically the image of pre and post this event, or just the post one if that's enough, and manually labeled for a few of them, so you can train your algorithm on that, and then you can use that algorithm on new data that you haven't seen at all.
Okay. I don't see any reaction from the participant online.
Right. Another thing that could be played around is like right now we used 4 channels, and we selected these channels quite randomly, or like. But what happens if you use all the 11 channels? Maybe using more channels is basically more information to learn from. Of course, it means also more parameters to fine-tune. So sometimes it can lead to difficulties into learning, especially in the first layers. If you have 11 channels that are mapping to 64, you might increase by a big fractions actually the number of parameters that you actually need to learn. So it might be a bit more challenging when you have more channels, but you can play around with these channels. And if you have some prior knowledge knowing that these are the channels that are really impactful for that, you can actually handpick those channels to represent your needs. I do imagine that the near infrared is very important, the SWIR as well maybe, and if you learn to combine those channels, it's actually a nice way to improve further the performances.
Nobody has done that yet in the papers?
That's a good question. I think they only use the 4 channels. I'm not sure if actually, maybe it was actually the best performance, but maybe on the 11 channels. I have to double check that paper. I don't have that information right now.
Because that would be interesting to see the sensitivity of all these 11 channels, because some of them are correlated and they provide more or less the same information, but to see which one is more appropriate. But physically, we know which one would be more appropriate. But to see if the system is able to do a sensitivity analysis on that, to identify which channels are the most appropriate for.
I think the sensitivity analysis could be simply like feeding like one channel at a time and just learning how to process that channel with a deep learning architecture, and analyzing how performant that is eventually, and the more performance, the more information is contained in that channels, and then combining the most performing the more performing channels together would lead to even better performances for sure.
But if you want to identify different type of feature, because here is like either warm or no warm. If you want to identify different type of features, it's better to do it one by one. I mean, training for one, trying to identify a feature, or you can also place like labels that has many different values and train.
You can technically like put like all the different channels and just like understand which one and have basically one models that actually work on all the channels. But I think maybe like one better way to handle like the sensitivity or like how the component of a specific channel is important is basically going one channel at a time.
I'm talking about the channels. I'm talking about instead of having only burn, no burn, if you have different classifications, for example, land use cover.
Of course.
You can have a labeling that has many different type of features.
Right. Yes, absolutely. Yeah, here we only have like these two channels. In fact, all of those models are parameterized with the number of classes that I'm working on, and this is only have two, burned, non-burned. But if you have multiple classes, like for instance, if you take the CLC, the same dataset contains the CLC, the land use cover. You can actually learn that land use cover, for instance. So one of good exercise could be taking the same datasets, instead of using the labels for the fires, using the labels from the CLC, and actually train the models to recognize the different part of the different land use cover.
I was wondering if the number of the classes that you are putting into the model makes an effect, or if it's better to have like a low.
It makes an effect because like you are changing the whole problem altogether. If you are if you only have 3 classes of like water and I don't know, 2 other classes of land and maybe something else, vegetation, let's say. This task is easier than actually understanding the different type of vegetations. For instance, you might actually have, I don't know, 50 different types of vegetations that covers like maybe pine trees or different palm trees or something. You might be able actually to classify that, but of course the task becomes more difficult. Like how much difference there is between your classes can tell you how difficult is the problem. Usually, actually technically, more classes you add, the better. So if you have like, let's say 50 classes, rather than learning 50 models to just classify whether it's like a pine trees or a palm tree or water, it's actually better to have one model. Why is that? Because they actually have shared knowledge. Like for instance, me distinguishing what's the difference between a pine tree and a palm tree can also help me identify what's not any of these two. And you can actually identify that, well, if it's not any of those, it's water. Maybe the information of me understanding that this is a water area can help me understanding that's not pine tree nor a palm tree, let's say. So I think having more classes and having like a model that tackles all the classification together is better to actually tackle every single classification one after the other, because they have shared knowledge that can be used for that. One of the examples is the DVI, not the DVI, the NBR index. Maybe it was the DVI, I think Pietro mentioned that. For instance, it can be very sensitive of the water, where the water actually is. And actually it can trigger some really high index in an area that is the water. And that is something that, okay, you might overfit if you don't have the information that the water is actually is not a specific entity. But if you actually learn in your feature space that that's not a pine tree nor a palm tree, but it's actually water, that actually information can help you disentangle and specify the fact that, okay, I can help understand that fine grain. I don't know if I managed to answer your questions, but the short answer is the more classes you have, the more signals you actually can train on, and the better performances you actually have for a specific class.
We also take into account like the relation between those classes. Like, I mean, maybe where the pine trees are, there are also usually other kind of uses or whatever.
Right, absolutely. There's like right now we're also tackling also what we call the single class classifier, which basically means every single pixel is only one class. But actually there is like some other type of classifier called multi-class classifier, where maybe you can have multiple classes for that specific pixels. Maybe you want to train, I don't know, like a pixel can have multiple characteristics, for instance.
For instance, if you want to classify a forest, this is like a superclass, and then you want to specify which type of tree is in each pixel. And so you can have these different hierarchy as well in the classification.
Hierarchy is one, but also not like, for instance, if you want to classify, I don't know, temperature maybe, or pollutions, or cloud, and on top of that, land cover usage, a single pixel can have multiple values, multiple classes at the same time. So it can be like completely unrelated, but sometimes it helps identifying one distribution of classes can help identify the distribution of classes. And there's another use case which we have like a tree of information. So first, you might want a hierarchical tree. So at the first level, you just identify water, land, vegetations, but then the vegetation can be have an arborescence of like different type of vegetations, and you can go from coarse classifications to finer grained classifications. You can actually learn all those concepts at the same time by training multiple classifiers at the same time. That goes towards the task of multitask learning. So instead of having a single end goal, you have multiple end goals, and you train the same models to perform the similar, different tasks at the same time.
And these tasks can be very different. You can have segmentation tasks combined with a detection task, combined with generating some text, and all of them are going to bring information inside the model that come from either the segmentation mask, either some text, either some bounding boxes, and this can help also training the model.
That's a bit more advanced.
Yeah, that's a bit more advanced.
And you need to have data from multiple sources, so it's more difficult to access this type of data in general. In some cases, it makes sense.
I have another question. When you want to differentiate different type of vegetation, sometimes, for example, an oak tree has the same characteristic as a birch. The only difference is in the time. You will see the oak tree that's the seasonality comes before the birch. Is there a way to take into account that spatial temporal difference? Yeah.
There is a way. That way, I would say, could be the following. Right now, we are taking like 3 or 4 channels that correspond to multiple bandwidth, but actually those 3 or 4 channels could only correspond to one bandwidth in particular, but different moment in time. If there is a cyclic, for instance, of a per year cyclic, and I can have 1 image per month, for instance, I can actually create an image of 12 channels that represents maybe the near-infrared filters at January, February, March, April, and so on and so forth. And that signature, so its temporal signature, will be different from an oak tree or to a birch, for instance. You can do so. The thing is that the difficulty here arises that the more data you put in input, the more difficult it is to find the discriminative signals that discriminate between a hawk and a birch, for instance.
If you know it in advance, why not put it also directly as a signal into the neural network?
That's a good thing.
Right? If you know that the important part is the difference between March and April, and the difference between May and June, then just put those differences as an input to the model, right? So putting the raw data is when you don't understand the data that works. But you can help the model by already providing some if you know that these are the discriminative features, just put them into.
Because the idea is that the more data, the more difficult it is to find the information. And it's like looking a needle in a haystack. If you have something that is really a very large dimension of data, as we were saying, like an image could be like 6 million pixels if you have 3 channels that are very high resolutions. But actually, if you stack more layers, if like 60 layers, it becomes very difficult to identify which channel of the data actually contains the information you're looking for. So having some previous knowledge, like for instance, if you know that the near infrared is better than the red or the green, let's just focus on the near infrared data, because instead of looking at 4 channels of data, you only look at 2 of them. The more data, the higher dimensional of your input data is, the more difficult it is to find the trend in that data.
The bigger the model you will need, the bigger the data set you will need, and so on.
Good. All right. Any other questions?
No reaction from the participant online.
Actually, you can also, and I think that was a bit discussed already yesterday, you can also have kind of an iterative approach. So you would run your model, you realize which kind of confusion you are facing, and then you understand that you maybe need to teach the model with additional information, and then you run it again, and then you can progressively help the model to fit the reality.
Exactly. Yeah. So if you figure out that it's always having some kind of mistakes that are related to water, let's say, and you know that if you just put another map that is very discriminative compared to water, and you retrain on this data, and this is where your expertise can also come in handy. Yeah, of course.
All right. Good. All right. I have a last Jupyter notebook to show you. There is no hands-on here, but it's basically a practical how to use GeoSAM because there is like some interest on GeoSAM, and there is a very good library provided by actually this one is called SAMGeo, I think. And there is a really good way to use it. So we need to use a GPU, and I think that's already running. I'm gonna go connect that instance, and this is part number 6 in that. Connect with our GPU.
And may need to stop other sessions.
Right, you might have to stop other sessions, yes. Actually, I actually reached maximum usage for today for myself on GPUs.
You want my computer?
Can you run it?
I'll check.
If you can share your screen, that would be better, yes.
Yeah, I can do that.
But basically, in that one, I'm going to run everything, run anyway. So here I'm installing the Python library called segment geospace. And well, actually, if you run it directly, I have some. I don't have the interactive. You can?
Yeah. There you go. Okay, it's connected.
Perfect. So it's connected. Perfect. So here I'm running step by step. Just de-zoom a bit. Okay. Okay. Not my laptop, so it's a bit difficult. But
What do you want to do? What do you want to do?
I want to click here.
Hey, you want to run?
Okay.
Step by step.
Yes, step by step. Okay. I'm installing the things. Very cute. Okay.
Yeah, sorry, mine is in French.
It's okay. Actually, I'm going to run like until 6.2. So here first, the SAMGeo, like is basically coming from here, is basically integrates SAM2 for precise object detection. It needs to run on a GPU, so you need to select the T4 GPU on the right, and install some library that might take a bit of time. Segment geospatial. That part of downloading SAM2 takes maybe 3 to 4 minutes. But once that's done, you can import a leaf map, and from SAMGeo you can import SAMGeo 2, and you can use leaf map to look at a specific GPS coordinate and a specific zoom at a specific resolutions, and this should actually appear as a map here. It will appear soon. Everything might run up a little bit sometimes. Just make sure you share my screen if you don't mind. Okay. So that's the thing, I already have run it at some point as well. Alright. So if you have installed that part, it takes some time. But then you can import a leaf map in SAMGeo and create a map. And leaf map is interactive tools that allows you to play with maps. And here in particular, I have. Oh no, it's actually not working. So I'm developing that. It takes some time. Sorry. Okay, it's loading. it install a lot of libraries in that Conda environment, in that Jupyter environment to basically have some geo ready here. I think you just need to cancel here. Perfect. Great. So now I can import leaf map, and I can also import some geo2 and create an interactive maps. That's going to be loaded soon. But the reason why I wanted to show you that is also because there is like this footprint of buildings to be developed very easily. Is it working well as well? Still downloading? Okay. All right. So this is how leaf map look like. So you can create the map, pointed at some places in the world, the specific zoom, the specific height, and just visualize that here. Then we can download a sample image here, saving to GeoTIFF, and then display the download image on the maps. So here I have downloaded like a specific maps from leaf map that shows me like that region in particular. That's with leaf map, and then I can use some geo2 to run that on the image itself and start segmenting the image. It's working on your hand?
It's still downloading.
Still downloading?
Takes a bit of time.
Takes a bit of time, probably. That's creating the model SAM Geo2 that is being downloaded in my workstation. All right, it's downloading everything. Anyway. All right, so it's loading everything. Is it working on your hand? Downloading the part, okay. All right, maybe I'll go a bit quick on that one because it will not work on my workstation, on my environment. But basically, what you're going to have at the end is a user interface that looks like this. So basically, on top of leaf map, you have the possibility when you reach like the bottom of that code, where you can click on specific objects of interest and just click segments. And if you just click segment, then you are able to get the segmentations of all the houses, for instance. That works with any type of semantics. It's the segment anything models that we have seen yesterday. And it's directly a plugin that has been, that's working quite well for satellite images. It has the limitation of SAM that we have presented yesterday, but it's a very powerful tool that can go, for instance, from points to footprint, like you were telling us yesterday. It could be like a quite interesting application. Is it working for you?
Yeah, I think so. Where do you want to? It's running.
It's running here?
Yeah. Depends what you want to show.
Let me first like
So what you explained yesterday is that actually SAM is segmenting everything at the time when you upload the image itself.
Right.
And then when you select, basically you just select the polygon that was actually already extracted.
And it takes around 30 seconds actually to segment everything on that. Actually, I might be able to run something already just on my workstation. Because I think it has actually segmented the image. I'm going to run that part. Then I add the raster of that mask. So even without GPU, it actually works. So here, for instance, I've created a few points, and from these points, I can actually select those 4 houses. So those are GPS points, the coordinates that are defined here, and I can extend them as a region here. The image is a bit blurry, still loading, but this is what it's supposed to look like. Then you can use a specific vector dataset as prompt for prompt that come from that specific source. So if I select basically the points of all those houses, I'm able to segment them. It's going to be running. Is it running for you? Yeah, this is the one, actually the one live here.
You want me to share the screen? Yeah. There we go.
So in that demo, for instance, so it has loaded a list of coordinates that come from that link here, and basically defined like all those points around the houses. It's like you can click on top of that, and it automatically creates like the masks out of it. So it could be extremely powerful for you to go from points to segments. It's based on the GeoSAM code. And it has quite a nice user interface. You can also interact with it and create, there's a function called the regularize, and regularize means going from, sorry, I'm a bit like, use Mac, and it's a bit, basically go from mask to footprint as a bounding box here. It's loading. Loading. And then somebody lost the rasterizer. Then you have an interactive map. Exactly, that's what I was looking for. So let's zoom a bit. I can select some points. But there's something wrong. For some reason, I lost the raster image. But I wanted to show you that demo live, but I have a feeling it's actually.
It happened to me as well, but I relaunching the
whole thing. Yeah, and load. I think run all actually works, but for some reason, like maybe like many people connecting at the same time is not like, like some bottleneck.
Yeah,
in the server. Like it's still loading.
Yeah, it's very slow.
But yeah, it was a cool demo. But basically, if you click on plus, you can select some.
That's okay. You click. Yeah.
You clicked. Okay.
Yeah. Right.
Then you click segment, or like add more points. Like click plus.
Plus.
Yes, like
I can click here, for instance.
Exactly. Yeah.
Plus.
No,
you can. I can leave
you
it.
can click multiple. Yes. Here.
There.
And then click segment. That will segment the house automatically. You can also try with roundabouts or with different.
Yeah, we can see them being highlighted now.
Yeah.
Yeah.
Good. All right. So that's an example of a library called GeoSAM that you can use and interact directly with your tools. And it's as easy as making it run on the Jupyter notebook. Might be sometimes challenging, but it's really good.
I think there may be a bottleneck of connection here.
So that was the last. Part of that hands-on, that workshop. So we covered in the second section of after the coffee break how to define the deep learning pipeline by creating data sets, by creating models, and how to train that models on a specific data set. We saw two models. The first model, which was DeepLab V3, which takes the post-fire image and just process them. And then we saw how BAM-CD worked by combining both the pre-fire and the post-fires. We haven't tried them until the end because it takes some time, but we have loaded some pre-trained models and validated that. And then in the last part, this part 6, is some extra that we have added, which is a tool for GeoSAM. That is an interactive tool where you can add points and create segments out of that. So in the same way, I told you like how SAM works. First, we actually pre-process everything, so it segments everywhere. And then when you click a point, it just shows some of these mask segments that you're actually interested in. The pre-processing actually takes around 30 seconds for an image and for a region as well. And then once it's pre-processed, you can just select what's interesting. You can see that as a super pixels. We were mentioning yesterday super pixels, but I do like to think that SAM is nothing else than a very fancy super pixel methods that creates different regions of interest that are shared similar semantics. And that has been applied then for geographic data and satellite images. Right. And that's it for us.
Very good.
Sorry, you maybe already mentioned that the satellite image, which one is it? Where does it come from? This is a Google.
That's good questions. I don't have that answer. That demo has been borrowed from GeoSAM GitHub repository. So I'm not sure where did it come from.
You can put the image that you want.
Yeah.
Yeah, I mean that's.
I don't know where that image. I think it comes from LeafMap directly. LeafMap is a tool to visualize maps, and it's called the base map. I think it's called the satellite, but I don't know which satellite it is. To be honest with you, it's an RGB, as we can see from here. I think LeafMap is also with OpenStreetMaps. It also integrates maybe some data from Mapbox as well, or they actually collaborate together. I don't know which one is the provider of which one, but this is the type of data that can also be accessed through Mapbox, for instance. Wow. So that's it. That's it for us. Thank you for your patience for this morning, and I hope you learned something. Happy to collect any feedback on this session. It was the first time we actually give that session for Earth observations. Thank you for your patience and for attending this class. I hope that will give you some tools in hands to develop your own solutions, and feel free to reach out if you have some specific questions that you still have some issue tackling. I'm very happy to brainstorm with you guys to basically figure out what the type of problem that you have and find solutions together.